Today we have here in the Department of Chemical Science of the University of Padua, Professor Zysman-Colman from the University of St. Andrews. So I want to ask you a couple of questions about your research. So we can find more examples about the photocatalytic application of molecules that present this TATF, let's say, behavior. But we can find these examples in electron transfer mechanisms, no? But when we try to design new photosensitizers, we don't have a lot of information about how can we modulate this energy in the triplet state. So do you have like an idea?
Yeah, so I would push back against that. I would say that, all right, the subset of molecules, organic TADF molecules that have been looked at for photocatalysis is very small. The number of TADF compounds that are in the literature numbers in the thousands. And so they've just been used for other purposes. So there's a lot of data out there for those molecules, and you mentioned triplet state energies as one parameter, where that information exists. It just exists for other applications. So I would argue that there's actually a humongous wealth of information that allows one to grab photocatalyst 1 with triplet energy 1, and if you want triplet energy 2, there'll be another photocatalyst, there'll be another compound that could act as a photocatalyst that would have that triplet energy. And so I think the wealth of available photocatalysts is huge. And hopefully what the presentation today showed is that we repurposed, I think I showed 3 different examples of molecules that originally had been conceived for OLEDs being used as photocatalysts quite effectively, where we knew the properties in the OLED context first, and we recognized their potential, and then we translated that to photocatalysis.
Okay, about the mechanophotochemistry, no? That is the hot topic of the day. In your opinion, which will be the next generation, no? If we want to extrapolate mechanophotochemistry, for example, in large scale, let's say, see which technique maybe can help us to design better, see the reactivity or the reactor, no?
So first of all, I would love it if more people, I mean, we published this earlier on this year, so I would love it if more people got on the bandwagon and what we showed really leads to a large change amongst the community that does photocatalysis. They went out and got a ball mill and then used some of the designs to show how much even more general than what we've shown. That would be fantastic. So I hope it takes off. The second part, which related to scale up, I alluded to in the questions and answers that our envisaged solution is to use extruder technology and to adapt that, much like we found technological solutions in the ball mill case, we can have technological solutions there. And so I believe that there is a large-scale version of what I showed today that is able to work, and our preliminary unpublished results seem to suggest that this is good. You need to have a large-scale solution if it's to be practical, right? In the solution state case, it's flow technology. That's what works. So we needed to be able, in order to really sell what we were doing, we needed to provide a potential solution that likewise would work at those scales. And so I hope that maybe by next year we'll report.
Okay, fantastic. So thank you so much for your wonderful talk and for coming. It's a pleasure for us having you here.
Thank you very much.